How do airplanes fly? Hey there, welcome to this lesson. Today you're going to learn how airplanes fly. The object of this lesson is to give a basic understanding of the principles of flight. These can be applied to a variety of machines, but in this lesson we will talk about airplanes, because that's what we're here for, right? So this is the airplane we're working with today. We're looking at a single engine airplane, which is easy to maneuver and, trust me, fun to fly. So let's start with some basic terms. Fuselage. This is the body of your airplane, where passengers, baggages, and the flight crew sit. Wings. We all know this one, but it's good to point them out anyway. Just to be on the same page, you generally need two to fly, one on the left side and one on the right side. Vertical fin. If the inspiration from wings comes from birds, this one comes from fish and helps with stability. Horizontal stabilizer. Just another set of smaller wings down at the back, helps with control and stability. We'll go into more depth about how and why we use them later in the session. You need three things to keep you up in the air: a good shape of the wing, speed, and, go figure, air itself. So I thought I'd put this up for you to meditate on: the formula of lift. This bunch of numbers and letters can be very entertaining if you speak the language of fluid dynamics. However, for now, I'll keep it simple and hopefully give you a good grasp of its meaning. The three things mentioned earlier can all be found in this formula: a good shape of the wing, speed, and air. Let's talk about air first. This is a very interesting element when it comes to make an object fly. On one end, it's essential to get lift. On the other end, it produces resistance to the motion of your object. In both cases, the denser the air, the stronger the two effects are. So, better lift and higher drag. Lift can be thought of as a difference in air pressure between the lower side of the wing and the upper side. So, the denser the air, the more molecules make up the air, the stronger the pressure difference can be. The drag is much easier to understand. Just think about how much harder it is to move in water. The higher density is what makes you feel more tired. We'll explain very soon the reason why, but trust me for now. You need the air in motion around your wings to make them fly. In other terms, you need speed. This is an easy one to understand if we all agree that lift is a force. If you walk or run towards a wall, the result of the impact will be different. You are the same, the wall is the same. What changes is your speed, walking or running, and obviously the level of pain you feel afterwards. The last element of the formula of lift is the shape of the wing. There are many aspects to it: surface, length, thickness, curvature, and so on. But there is one I want to talk about: the airfoil. If you imagine slicing the wing and looking at it from the side, you see the airfoil. Airfoils come in a huge variety of shapes and can even change between sections of the same wing, but they generally all have a slightly rounded top and a relatively flatter bottom. But what's so special about this particular shape? To understand that, we have to talk about something else first: the equation of continuity and Bernoulli's theorem. We have all experienced the equation of continuity when we use a water hose. If you tighten the nozzle, the water will flow faster. The reason for this is that the same quantity, in this case of water, has to come out in the same amount of time. If we reduce the area of the opening, the speed of the water has to increase to achieve this and respect this principle. The same would happen if we swap the water with any fluid, including air in this case. Bernoulli's theorem can be trickier to understand, so this is all I'm going to say. When a fluid flows at a higher speed, its pressure diminishes. We can now go back to the airfoil. Let's imagine a rectangle around it. There will be air flowing in and out of it, and if we think it to be big enough, we are allowed to suppose that the air outside of this rectangle is not disturbed by the presence of the airfoil. Now, let's divide the rectangle into two sections. Before the air encounters the airfoil, the airflow takes up the same amount of space in both sections. Then, half the air will flow above the airfoil and the other half below. As you can see, in the upper section, the space for the air to flow through diminishes, whereas in the lower section it increases for the same amount of air. Thanks to the equation of continuity, we now know that the speed will increase in the upper section and decrease in the lower section. We can also have an idea of how the pressure differs around the airfoil using Bernoulli's theorem. Generally, we will have a lower pressure at the top and a higher pressure at the bottom. Remember, the higher the speed, the lower the pressure. Even if nothing is physically pushing the airfoil upwards, the difference in pressure creates an imaginary force that acts on the airfoil. So there you have it, lift. This imaginary force has been created from the airfoil just being there, disturbing the airflow. We can imagine our wings as many airfoils placed one next to the other. The three-dimensional world brings many more possibilities when it comes to the shapes, but also many more problems, so we're not gonna delve into that in this course. But the general idea is the same. Create a shape that, once placed in an airfoil, will disturb it, creating a difference in pressure around it that generates lift. Let's quickly go back to the airfoil for a second, so that you can better understand the next section. The angle between the airflow and the airfoil is called angle of attack. Even when the angle of attack is zero, the average airfoil is still capable of generating lift thanks to its typical shape discussed before. Lift increases the more we incline the airfoil until a certain angle of attack is reached. At this angle, the air doesn't properly flow around the airfoil, causing a sudden loss of the difference in pressure, determining then a loss in lift. This phenomenon is called a stall. The aim is to being able to modify the angle of attack to increase or decrease lift as needed, but avoiding to reach the critical angle of attack that makes the airplane stall, because, well, the overall idea is not to fall. Let's say that this airfoil is moving in the air. If we draw a line from the front to the back, we can see that the direction of the airfoil is the same as the direction of the airflow, making the angle of attack equivalent to 0. If we move the part at the back up, the line is now at a negative angle with the airflow. If we move that same part down, the line is now at a positive angle, which will equate to an increase in lift. How to maneuver? There are three directions you can move an airplane in. Up, down, called pitch. Left, right, called roll. And sliding sideways, called yaw. All these maneuvers are done by moving different surfaces of the airplane, creating a difference in pressure around them that makes the airplane change its attitude and subsequently its trajectory. So when a pilot decides that it's time to climb or descend, they have to modify the shape of the horizontal stabilizer. Right there at the back, there's a movable part called elevator. On both sides, you have an elevator, and both move the same way at the same time to generate a force that pitches the aircraft upwards or downwards. When the airplane goes straight ahead, it can be seen as if it was kept in level by two pedestals, one below the wing and one below the stabilizer. When we move the elevator, we can change the amount of lift the stabilizer generates, or in other terms, change the height of the pedestal. By moving the elevator up, the disturbance created in the airflow is reduced, thus causing a reduction in lift, or, as in our example, a lowering of the rear pedestal. To achieve a pitch down instead, the elevator goes down, creating a stronger lift force at the back of the aircraft, causing the nose to point down. The same concept is used to yaw the aircraft. Similar to the stabilizer, the vertical fin has a moving part called rudder that goes left or right. By applying an analogous idea to the one just seen, the rudder modifies the shape of the fin, generating a lift force that pushes the tail either left or right. The fin and the rudder are mainly used to control directional stability by creating a force that prevents the aircraft from yawing, or simply put, keeping it going straight. It also helps with resistance forces created by turning the aircraft. So by using the rudder, you can keep control of a turn by counteracting these forces. The rudder plays a fundamental role when trying to control an airplane that has lost one engine. Of course, I'm talking about an airplane with more than one engine. If you, let's say, lose the left engine of a two-engine airplane, you still want to keep the right engine on to, have something to keep you up in the air. But the functioning engine is now giving you a push forward that is no longer balanced on the other side. And this causes the aircraft to yaw significantly. This is why you need a big-sized rudder. Let's now talk about ailerons. These are movable parts at the back of the wings. You use them to roll the airplane and change direction. Differently from the elevators, the ailerons do not move in the same direction. When one moves up, the other moves down. If we see the airplane as once again sustained by two pedestals, with one under the left wing and the other under the right wing, the imaginary pedestal will be of the same height while the airplane is flying straight. The action of moving the aileron down on one wing and up on the other will determine a loss of lift on the side it goes up and an increase of lift on the side it goes down. Again, in other terms, one pedestal would become higher and the other one shorter, causing the airplane to roll. To finish this lesson, I wanted to briefly talk about the four main forces that act on an airplane while in flight. We have the weight of the airplane, made up of the weight of empty plane, all the people on board, baggage on board, and the fuel in the tanks. We have talked about the lift, mainly generated by the airplane being in movement in the air, which is also what causes another force, the drag. Finally, drag is counteracted by thrust, produced by the engines. By now you should have a clear idea on how airplanes fly. So what I have left to say is, see you in the next lesson. Bye!